like a very very quick introduction to text and metaprogramming with MetaStar. So the idea is that for like 20 minutes or something, I have 20 main slides prepared. I'll show you more or less what you're capable of doing with MetaStar, and then we go into do some demos and show you stuff more hands-on. There's also, as you might have seen in the channel, a new this is the idea of the talk. We're building a new chapter in the FStar tutorial that fully explains all this stuff. So if some details missing here, it's probably there already, or it's going to appear there. But feel free to ask at any point. I plan to go pretty fast in this, during the slides, and then I'm going to jump down to code, and then we can talk in a lot more detail. But feel free to ask at any point. So yeah, it's going to be a high-level presentation. We're not going to cover everything, and please see the new chapter that it's going to be on the website, but for now it's on the PDF in the channel because we couldn't get it to upload it. So anyway, the main uses of MetaStar. So MetaStar is a tactics and metaprogramming framework for FStar. The main uses, more or less in order of importance, I would say, is first of all, is simplifying or proving assertions or any kind of proof that you would like to have. It introduces a new syntax, assert by. So instead of just saying assert some proposition, you can attach a tactic to it to prove it, pre-process it, simplify it. We'll see a couple examples of different things you can do. The second big thing we do is metaprogramming. So automatically generating programs or pieces of code. This includes like just generating some new top-level definition of function, just generating some parts of it, or maybe generating an entire module, or taking existing code and specialize in it and this kind of thing. So if you're familiar with ever parse, it makes heavy use of this to generate the verified parsers. It's also used as it can also be used to solve implicit arguments. So like to give a custom strategy to solve implicit arguments, and this is what we use to implement type classes in FStar. And I'll show you a bit of the details of how that's implemented. And I'm not going to say a ton on this, but it's also used to do program transformations. So you can attach a tactic to modify a program after it's type checked, say at the time of extraction, normalize it, simplify it, and say do some verified transformation on it. So okay, let's go to proving, which I think it's what most people are interested here. So you're all familiar with FStar, but let's briefly go show how the process is of verifying something in FStar. You usually write the program, it goes through the type checker, it generates some verification condition. I'm calling it V here, and it's encoded to the SMT solver, right, as a verification condition in the SMT language, the SMT2 language. And then if C3 accepts the verification condition and says, yeah, this holds, then your program type checks, right? And everyone's happy. But the problem is that when C3 does not accept the thing, you need to go and modify your program, maybe add a few lemma calls, add a few assertions, and then hopefully you get C3 to accept your program and then your program type checks, right? And this works rather well, right? There are possibly all of us have done very huge developments in FStar, where this is the style of proof that we do. So C3 is surprisingly, C3 and the encoding are surprisingly capable of doing many things. And normally all you need to do is give the key and set via lemmas. But at some point you start running into a wall, right? For instance, look at this rather simple lemma modular addition. And you would like to prove it like this and just leave it to the SMT solver. But it turns out, and this is a proof that it was actually in the FStar library, you need a bunch of lemma calls and to guide the solver really deeply into how to find the proof. And this is still kind of readable, right? But it's already counterproductive. It takes a long time to write this kind of thing. And also the idea of the proof is pretty lost, right? You don't see what's going on here. You just see like all the things that the solver happened to need. In some more complicated examples, there's really no way you would do a manual proof or a proof of that style. This is taken from a lemma on a verified implementation of Poly 1305, and this assertion here at the bottom that involves all this big arithmetic experiments involves like 41 steps of distributivity and associativity that typing by hand would just be way too much work and way too error prone and possibly turn you insane. So MetaStar is so this is practically not the way to do things. So MetaStar is a way to do something different, and the usual goal of a tactics framework is to automate the generation of proofs, right? But here we're not going to really automate the full generation of proofs. We just want to pre-process them, massage them, do something to them before going to the SMT solver. Yeah, so the most common examples of this kind of thing are, well, we just want to like pre-process or solve enough star, all the things that are hard for the solver, right? We're not going to do like just normal propositional logic, because the SMT solver is fully capable of doing that and very, very fast. So one of the most common examples that we have is canonicalization of arithmetic expressions, because when you go to like nonlinear arithmetic that's undecidable on the SMT solver will usually not work very well. We can also like simplify via calling lemmas to rewrite some parts of your proof obligation into others, normalize them, unfold symbols and this kind of thing. Maybe split into cases, or just like touch the solver's options, right? Like instead of using all of the lemmas available to you to prove this particular assertion, just prune the context and let C3 work on a reduced set of axioms that you know is sufficient. That said, it's still possible to fully automate proofs and just do it completely within F star and not use the SMT solver. We'll actually see a couple of simple examples of doing that. So far, is everyone with me, I guess? So this is what ideally would like to write for the previous lemma that I showed you, this one on screen, right? Instead of giving this assertion to C3 as is, we attach this by keyword with some tactic here to pre-process this assertion. And in particular, this tactic, which it exists in F star, I'll show you this running in a couple of minutes, will canonicalize both of these sides of the expression. And after it, the proof of this assertion will end up being trivial, and C3 will prove it super fast, super reliably in a matter of seconds, probably. We've actually measured at some point that when doing this simplification and then calling C3 with the simplified proof, the whole process was super fast compared to not doing anything, and like it was being proven 100% of the time. While with the original assertion, even if you raise the limits to like 100x of the default R limit and default time, it would still like maybe work 20% of the time or something. So it's a matter not only of saving on programmer time, but also on proof robustness, right? By adding this kind of simplifications, you get proofs that are much more robust and will not break just through some random changes. So the way this thing works, more or less, when you add when you attach a tactic to an assertion, what happens is basically that imagine this is the full VC for the definition you have. It's really a huge logical formula. And say in the previous case, you had an equality. And when you add an assertion, you basically get, okay, you need to prove that what you're asserting is true. And then you can assume it in the continuation of whatever else your program needs to prove, your post condition, let's say. So assertions essentially introduce a logical cut in the verification condition. But by attaching the tactic, what's going to happen is that this part is not going to be there in your verification condition. And instead, you're going to get a goal in meta star that you need to prove. Right. So this is taken out, and now C3 can really just assume the post condition of the assertion in the following, like in the continuation of your program, in the rest of your program. But you have to prove it via meta star, and you get a goal which you can transform in many ways. And at any point, you can also say, okay, I'm tired of this, I give up, and give it to C3 as well. But it has to be proven in one way or another, either fully manually or by giving it to C3 again. And you can kind of switch back and forth between these two views, between a piece of verification condition and the goal in the sense of a tactic framework, which in this case, it's saying you need to prove that L equals R in this context, where you have, the binders here and some hypotheses that you gather as you traverse this formula. And for instance, in this case of canonicalization, what we will do is, first, without having to prove this assertion, if you can just assume it, this verification condition turns out to become trivial. So C3 can really just prove this and knock it out of the park. For the second one, we run the tactic, this canon semi-ring that I'll show you in detail a bit later. It will normalize or tune to canonical form both of the sides of this equality here. And once that's done, and this whole process is verified, of course, this reduced goal, this normalized goal, is also handleable by C3 super trivially, super fast, and robustly. So that's basically the high-level picture of what happens when you attach a tactic to an assertion in meta star. Now for tactics, so I've shown you like a very simple call, this canon semi-ring thing that looks a bit magical right now, I imagine. We'll see a bit how it's implemented in a while. But metaprograms are really just F-star programs. Metaprograms and tactics, I use the term rather interchangeably right now. They are F-star programs that can do some manipulation of this proof state of the goals and simplify and do this kind of thing. And they are embedded in F-star as an effect, right? Just as exception is the effect for exceptions, we have tag that is the effect for metaprograms. And the only thing you can do with these is run them via meta F-star to simplify a proof state, to generate new programs, to do proofs and this kind of thing. Morally, they are kind of like a state monad over a proof state. Like you can think of the proof state as the set of goals that you need to prove. And you also have exceptions in it. Your tactic could fail, and that's fine. If your tactic fails, then you can recover and try another path, like do backtracking, or you'd also like fail to type check if your tactic raises an error that you don't catch. So this part is completely standard. It's really just a state monad with exceptions and also divergence. So metaprograms don't have to terminate, which if it's the first time you hear this, it might sound a bit weird because in independent type theory, if you're doing proofs, you usually forbid non-termination because non-termination usually implies the proof of false. But this is happening at the meta level. So if your meta program, if your tactic never terminates, then you never get to type check whatever it is you're checking, and you won't get a proof of false out of that. So just a tiny detail for someone, in case that meant anything to anyone. So okay, this part is standard. There's a proof state and exceptions, and there's some assumed primitives, right? So this is a bit of detail on how it is implemented. This is really just a state monad. Don't really need to understand this at this point. And there's a set of primitives that actually operate on this proof state, because the proof state is something abstract. You cannot just do anything you want with it, because we need to ensure that whatever transformation you do to the proof state is sound. Like you cannot just say, oh, well, forget about this goal, I'm not going to prove it, right? F-star needs to check that everything that has to be proven is actually proven. So you have a bunch of primitives like exact and apply, which solve goals in different ways, introduction, to move across binders. You can type check terms. You can also raise exceptions and catch them and do all this kind of stuff. All of that encapsulated within the tag effect. If you use any of these, you need to be in the tag effect, and you can only run those things when you are doing proofs. So for a few simple examples of meta programs, like you just write them in direct syntax, right? They look just like F-star programs, just that they have some particular effect. So for instance, this meta program here, if you don't understand them, I'm going to show them examples live in a while. But it's really saying, okay, the goal is an implication, then, okay, introduce the implication, we get a hypothesis for that, rewrite it, and then apply some lemma called mylem to the goal. And you just write them like this in applicative style. You can also write combinators for your meta programs. For instance, this repeat takes a meta program that takes a unit argument and does something with it, and just runs the meta program again and again and again until it fails. So when catch T returns in left, it means that it failed, and you get the empty list. And otherwise, you get a result, and then you keep repeating. So you run it as much as you can to get a result. For instance, you could do repeat intro and gather all of the binders in your goal into their context and get them all as a list. And this is really just standard F-star, right? You can also use exceptions, and in this case, you can define exceptions just as you do for the Exon effect. You define exception like this, and then, whoops, sorry. And then you use raise and try with, right? And here are some ways of inspecting the goal that I'll show you a bit in a while, but this is the way you get your hands on the current goal. You can call core goal, and you get a term representing what it is you need to prove at this point. And so your meta program can decide what to do. So for instance, this for all intro is saying, okay, I'm going to look at the goal, and I want to display it as a formula because there's many ways to look at a goal. And if it's a for all, then I'm going to do this thing and return this binder intro. And if not, I'm going to raise an exception. So this is the implementation of for all intro, I think exactly as it is in the library right now. And also you can use anything already, any existing F-star program that's pure exceptions or divergence. You can already use them in meta F-star. So for instance, you can call into toad base exists B to traverse a list and do something with it. This is all legit. All of these effects are included in the tag effect of meta F-star. So, okay. Yeah, I'm going a bit fast. I'm going to show you some examples in a while. Sorry if your heads are going dizzy. I'll show you just a bit on how metaprogramming is done, like how you generate terms via MetaStar. So, for instance, besides this assert by keyword that attaches a tactic to an assertion, we have this variant or this other invocation of fstar, underscore by. And when you type underscore by, fstar will try to solve this underscore, right? If I don't put anything here, then fstar cannot really solve this underscore. There's nothing to unify it or anything. But when you attach the by, so metafstar runs, and the goal is to generate a term of this type. So in this case, this is a very roundabout way of generating the term 1 here as a definition, because this metaprogram is presented with a goal of providing a term of type int, and we solve it by exactly returning the term 1. And this way, the second way here is, again, a roundabout way of defining the addition of 1 plus 2. So we apply this plus operator, and this plus operator has 2 hypotheses. So now we get 2 goals, and we've got exact 1, exact 2 to solve these 2 sides. So this defines really just 1 and 1 plus 2. You can also do more complex stuff like defining, recursively defining very big pieces of syntax. And this might not be so interesting here because you could just type them out. This becomes quite interesting when you can actually inspect what you need to prove, or sorry, not prove, but what kind of program you need to define, what kind of term you need to define. For instance, in this case, we have this tactic called mkprinter, which you can call it with a type, and then say an inductive, and it will automatically generate a printer for it because it inspects the shape of this type, traverses it, and generates a function to print it automatically. So in a way, it's like deriving show in Haskell. It's the same kind of idea, except that we call it explicitly in this way. So for instance, from these few lines and the definition of mkprinter that we have in fstar, you can just call this, and you get a function called t1print, defined, well, it doesn't really matter how it's defined, but it basically matches on the thing and prints the name of the constructor and its arguments, and it even works with recursive constructors with actual inductive types. So in this case, it will print the subterm of type T1 here, calling itself recursively. Okay, and another use kind of related to this metaprogramming stuff, but not so much as generating a full program, but more like completing a part of the program that you wrote, is that metaprograms can be used to define custom policies for resolving implicit arguments. For instance, take a look at this function. It's called dag for diagonal. And it takes an integer x and an integer y, which is marked as implicit, and returns the pair xy. If we don't provide anything here, if this was just a normal implicit, then there's no way to solve for y. And this will just fail every time you try to use it, and you need to give this implicit argument explicitly every time you call it. But by attaching this same as tactic, which has a very simple definition, it's just like exact of this, what you can do is have y be automatically solved to x every time that you don't provide it explicitly. So if you call the act 42, you get 42, 42. If you give it explicitly, then there's nothing to be solved, and you gave some other choice for it, and okay, then we do not run the tactic. But if fstar cannot find the argument automatically by unification as usual, it will call the tactic and do something potentially custom with it. You can do anything you want here. So with this very same idea, these last 2 ideas that I show you, is how we implement type classes in fstar. So there's a module. This is completely user level, except for the syntax. That is just like some parser modifications, some sugaring modifications. It's really just completely user level. So there's a module fstar type classes in Hewlett. It defines 2 medium-sized tactics. They're not really big. One for creating a class, and one for solving the implicit arguments of like constraints, like typeless constraints that you use in functions. So once you have this, let's say you have some module called mymod, and let's say you want to define a class for the side level equality, and a class, or let's say just a record for now. This record contains a function, the comparison for equality, and this same record contains the proof that your equality function actually corresponds with propositional equality, so it decides propositional equality. then you can call this MK class tactic here, which I'm not going to show the definition, but it's rather boring, but it really just derives, it just writes this type and writes a few methods and marks it with some attributes. It doesn't do anything fancy at all. And then you get, from this splice call here that generates some definitions, you get EQ, which is a top-level function that is basically the projector for this term, for this field of the record. And it takes a term of this record type implicitly, right, via this TC resolve tactic, and returns the EQ field. And this one returns the EQ OK field. So this you can already define, right? This is easy to define by hand. You just do d.eq. This is a definition of this one, and d.eq OK is a definition of this one. It's an implicit argument that makes them interesting. So we have custom syntax for this. Instead of writing like the record type and this call to splice MK class, when you write class, that's exactly what this means. The sugars to this you're seeing right here on screen very quickly in the pipeline, very, very early in the pipeline of compilation. And we also have syntax for, instead of calling, of writing this hash TC resolve implicit qualifier in every argument, we can just write this. So I think this is the old syntax actually. It's braces and the bar, right? To mark a type class constraint. So it says EQ and EQOK have a type class constraint of the EQA, and they give you this kind of thing. And this really just means that this is an implicit argument solved by the TC resolve tactic. And then defining instances is really nothing more than declaring a record, right? So this EQ int is a record with an equality for integers and a proof, and that is marked with some particular attribute called TC instance. And we have special syntax for this as well. You can just write instance instead of the attribute and the let, but it's really just the same. And all of this works via meta start. It's mostly user level. Besides this, the sugaring syntax that I've showed you, it completely goes via meta start. And you can potentially do anything else that if you have some kind of strategy for resolving implicits, you can do it yourself in your own modules. So okay, now for something more, maybe a bit more hardcore, let's go into some more details about how canonicalization works. Let's say we have some complex expression, some goal that involves, say, concatenation of lists. I'm going to use a simple example here, which is lists, which form like a monoid. So we don't need to do anything too fancy. But in this case, like any human looking at this goal would just like ignore the parentheses, ignore this empty list, and see that these two are equal, right? So we'd like to conclude that they're equal pretty easily. In the case of lists, you might be able to give this to C3 and it will conclude it easily, but we're looking for a generic or a general solution here. So by applying the stuff that I kind of blew past before, but say application and inspecting the syntax of the goal and all this, you can already just use these lemmas that we have here, like associativity of lists of just 3 lists, like the most simple associativity, of course. And the fact that the empty list is a neutral element, and just apply this and apply congruences to each side and build a proof in this way. And we could do that by hand, right? We would just write, oh, apply this lemma, apply this lemma, apply this lemma. And you can build a proof of this. The thing is that that's way too slow. And we don't want to do this by hand. We don't really gain much. So the first idea we have is, okay, let's write a tactic that inspects the goal and decides which one of these lemmas to apply by looking at the shape of each of the sides of this goal. And you can do that. That's rather easy. And I think we have an example in Bulib also of a canonicalizer that works in this way for integers. The problem is that it's very slow. It's very slow because at every step that you're applying a lemma, you have to call into the type checker and you have to call into the unifier. And that, well, you basically pay as much as something proportional to the size of the term. And it's really not efficient. And in some other proof assistance, so what I'm going to show you next is a technique called proof by reflection, which I'm sure many of you know. In other proof assistance, this is also a question of the size of the proof. That's not really a problem for us because we don't store the actual proof term anywhere, but it's still way too slow to use. So the idea of proof by reflection, and this is going to be a very, very fast slide, is to, let's say I'm focusing on the problem of canonicalizing expressions of just lists with append and the empty list, right? So the first thing we need to do is build a data type for the AST of these expressions, for the abstract syntax tree of an expression of this shape. And we can detect represent concatenation of lists with this app node. App is for append. Nil, which is the empty list. And at any point, we can also say, okay, this is an atom. I don't know the structure of this. Maybe it's a variable. Maybe it's some fixed list, like 1, 2, 3, that doesn't really fit into this language, but it's just anything else. And in this case, we just like cop out and say, okay, it's an atom. I don't know what it is. So this is just a way to represent the syntax of a list expression appearing in your goal. You can also define a function, a denotation, that takes one of these expressions and returns a list. That's quite easy to do, even if you don't know anything of what's coming forward. In the case of an atom, well, that's really just a list A, so we already have the list. If it's an append, then we recursively call ourselves and concatenate the result. And if it's an empty list, we just return the empty list. And once we have this, this expression, let's say language or representation, we can define a canonicalizer of these that, let's say, just puts all appends to the right, just right associates everything and puts them in normal form. And we can define this just purely, right? We can define a pure function that does this. Let's say this val canon of expressions into a list of atoms, right? Because once you unfold everything and let's say, okay, if append is associative, why do I need to keep the structure? You can just put it as a list, right? And drop all the nils. So the normal form of a monoid, in a way, is really just a list of its atoms, of the atoms that appear in the expression in that order. And for this function, we can prove a lemma. Again, purely, there's no meta star here so far. We can prove a lemma that says, okay, if you denote, if I have an expression that denotes something, and I canonize the expression, then they denote the same thing, right? This canon does not really change the shape of, does not change the meaning of whatever it is that E is denoting, right? So, and that's intuitively correct, right? Because this canon would really just flatten this tree, and remove all nils and flatten all app nodes, and then you just have this list of atoms, which is really what matters. And it doesn't matter how you put them back together because append is associative, then this should really hold. So once you prove this, once you do a bit of work to get this going and start and prove it, and there's a very different style of proof that is not repeatedly applying lemmas, but it's really just relying on normalization to call this canon function and make it work blazingly fast. So let's say the goal is this simple thing. I chose a very, very simple goal to make it fit in the slide. But let's say we have to prove this, which is just a basic, just an application of associativity. But let's go via this procedure. The first thing we do, and this is where we rely on Metaprogramming to inspect the syntax of the goal and check, okay, it's an equality, and here's an append, and they're associated in this way. Metaprogramming can build a representation of these terms, a reification of these expressions as syntax in this type, right? And we can turn this goal to, so maybe be more explicit, we can turn this A appended to B appended to C into this ASD here, app of A prime, app of B prime, C prime, where A prime, B prime, and C prime are just val nodes for A, B, and C. And if we denote that, we get exactly this by the definition of the node. The node just really goes, descends on this type and calls append, like this add for every app node, and vice versa. And similarly for nil and for val, it just drops the val, and you get exactly this. And for the right-hand side, you get exactly this as well, right? So far, we have not really changed our goal a lot, because if you unfold this node, then you really get exactly this. So I guess that's a justification for why this is sound. But so far, there's nothing really surprising. But given that we have this lemma that the canonization is correct, we can turn this goal into this one, simplify it into this one. Because really, so the node of this thing, it's really the node canon of this thing by this lemma, right? Where E just takes this place, just takes this value, sorry, app A prime, app B prime, C prime. And once we have this, well, we can forget about the node, right? If we can prove that canon of this is equal to canon of this, then we're done, right? Because the node is a function, and if you give it the same thing, it's going to give you the same thing as output. So now our original goal gets reduced to proving this, that canon of this expression tree is equal to canon of this expression tree, right? And once we run canon, so here's the trick. Now we have to run canon, which is just a pure function, and we can simply run it. Just call the normalizer to run it, and we don't have to apply any lemmas. We have already applied all the lemmas that we need. So when you canonicalize them, you get something like this. Actually, I now realize it's a mistake because Canon was a list of atoms. So here it should be the list of A prime, B prime, C prime instead of this normalized node. But very super briefly, this is the idea of a proof by reflection. You build some syntax for the stuff you want to prove. You prove some kind of lemma relating the syntax to the semantics of the thing. And then most of the proof, most of the heavy lifting goes by a normalization, goes by this thing, which is just computation. If you call the norm primitive in F star, it will just prove this by a grunt work. It doesn't have to do anything fancy with the proof state or anything. This is really just like a pure computation. And if your goal is like hundreds of atoms long, this is going to be blazingly fast compared to the previous approach that I mentioned. So okay, that was my super quick intro to F star. Now I want to show you some how it actually works in maybe do a small demo, right? Because I'm sure that wasn't you're not going to go and write F star right now after watching that. So yeah, we're writing a chapter on Meta F star for the tutorial. It's probably going to appear this week, but I guess if we solve the CI thing, otherwise you have the PDF in the channel. So yeah, if you have any questions, I can answer them now, or we can just diving into the code and then you can ask, or however you prefer.
First of all, thank you very much. That was very insightful. Next, yes, I'd love to look at the code. Whichever you prepared is fine, and probably I'll find most of answers. Well, at least the most of questions I currently have in mind in your tutorials. So it will probably not wise to go and ask about technical details before I look into that, right?
Sure. Let's dive in then. I'll give you a quick
sure.
overview of most of the things that I've shown you. So this is a small module that I made for this talk.
I'll be okay, even if it will be not a quick overview. Just I'm ready to listen for as long as you could speak.
Okay.
Go ahead.
So this module, I just made it for this presentation. I could upload it later if you want, if people want. It's also most of it's taken from examples, already existing examples in tactics. But so to begin, anytime we want to use tactics, we need to open this module. This brings all the relevant names into scope, and then we get the tag effect, right? And here are a few non-interesting examples of tactics. They are really just using the tag effect. Wow, this is pretty slow when using Zoom. They're really just using tactics in not very interesting ways. So for instance, this is a tactic that does nothing. It just returns unit. This is calling into the length function of F star, like the total that computes the length on the list. Here's a quick example for recursive tactic that doesn't do much and terminates, and this is a recursive tactic that doesn't terminate. There's also here's like a small way to run a tactic to debug it without any goals. There's this run tactic marker, and then you can give it a tactic or a metaprogram inside this argument, and observe the effects that it has. So for instance, the dump primitive, you give it a string, and it will print the current proof state on this Emacs buffer, on the F star goals buffer on Emacs. So in this case, when you use run tactic, then it really starts out empty. So there's nothing here, but we do see the message that we had, so we can use this to maybe debug or get some information. So here's a first tiny example that I guess people who come from, say, Coq will be very familiar with. Let's say we're trying to prove this implication, right? We're going to do.
Sorry, may I have one question right now?
Sure.
This dump hello world, the function dump takes not just strings, but I presume any symbol, like it can dump a complex object.
No, not right now. It takes a string. You can turn most of them to strings. So, for instance, you can turn terms to strings by a primitive in.
Oh, there is something that would provide a string representation of some complicated object.
Not out of the box for anything. You might need to write the printer for the thing you want.
Oh, okay. Okay, sorry. Go on.
All right, so let's just go over a simple proof of this implication and a constructive proof of this implication. So this lemma saying that if you have A and B, then you have B and A. Not very surprising, maybe, but so we have this assertion here, and it's decorated with this tactic. And well, people familiar with Coq will really see this quite familiar, I think. So this is doing two calls to implies intro. We obtain the do hypothesis. At this point, we get as a goal this conjunction. We split it. We use the hypothesis, and then we're done. But of course, you cannot follow that what I'm saying because we're not seeing the proof run. So we can use a little option here. So we could put dumps throughout this proof to look at the proof state as it evolves as we perform some modifications to it. So for instance, so maybe it's obvious right now, but we don't have a really interactive mode for tactics in FSTAR. So we do have to write them all and then check them again, as you just see me do, I guess. But we can add this message print into to see what's going on behind the scenes. So here, after the original goal is of course this one: A implies B and A. After we do implies intro, we have this state where we have a hypothesis of A and we need to prove B implies B and A. If we move forward, after another implies intro, we have two hypotheses for A and B, and we need to prove this conjunction, right? And the split tactic, what it does is if we need to prove a conjunction, it will split into two separate goals. So after doing split, we need to prove B, and then we need to prove A. And so we use the hypothesis HB to prove B and the hypothesis HA to prove A. Sorry. And we can do all this manually by keeping track of the hypothesis and doing it by hand, or we can also just call into assumption, which is another custom tactic that will just look in the environment to find if something proves the goal that we want to prove. So this assumption will just find the HA and the HB automatically. So now for a maybe more interesting example, and one involving that.
Guido, what was up with the set command? Can you explain what it was doing?
Oh, sorry. Yes, I didn't run it in the end. So we can run this set options command to set this option tactics trace equals to 1. Let me just do a push options. And when you do this and you evaluate the tactic, you get a full trace of the things that it's doing. Right. So I get to inspect the state in between each successive call, basically at every semicolon or every let bind or every let in. Sorry, without having to write an explicit dump call. So it's a bit of a canon because you use it and you see it everywhere. A bit of a bazooka, I mean. And one is the depth of the tracing. So here we're tracing like this top level invocation, but we're not tracing inside these functions. So it's a bit of it's something that you can use to debug, but not something that you should probably rely on too much. Does that make sense?
Yes, thank you.
Okay. So here's an example that C3 can actually struggle with. We're trying to prove something very, very simple, that if X is less than 19, then 2 to the X is less than 1 million, right? And really, the most it could be is 2 to 19, which is this, but it's hard for C3 to figure it out. So, of course, maybe I should have started with an empty proof and see if C3 can figure it out, but it doesn't. And well, maybe the way the proof should go is, after thinking a while, is saying, okay, well, 2 to the X or POW2 is an increasing function, and I know that 2 to the 19 is this. So, well, then I should really have that 2 to the X is less than this, which is less than 1 million. Right, and the problem here is that, well, for one, C3 cannot prove this this implication here, this quantification, and it also cannot compute this. And we should be able to we should try to compute it within FSTAR to make it work. We expect failure here to get to move forward. Expect failure, in case anyone is not familiar with, just checks if this definition fails, and when it fails, it will accept it, and if it doesn't fail, it will raise an error. So you can check that something fails. So for the first part, for this this increasing function stuff, we really just need the fact for 19 and x. So we can call into this lemma that we have in method lemmas. And we can also prove this via Metaprogramming, but I don't really want to get into that many details right now. I want to see more what we can do with this following part, because even if we state that, okay, we know that 2 to the x should be less than 2 to the 19 because we have this lemma, we cannot prove this bit, right? That pow2 of 19 is that number. So the way we can do that by a meta star. So it's just calling into the compute tactic. So here we're tagging this assertion with the compute call that is just going to say, okay, reduce this goal as much as possible before encoding to C3, right? In this case, we do have the proof working and working quite fast. And if we print the state after the compute here.
One question, if I may.
Sure.
What will happen if you replace this assertion that fails with assert norm, assert underscore norm? Will it get accepted instead?
Yes, it's similar. This is a slightly different way of achieving a similar effect. Yes.
But it will work, yeah? I was just asking because sometimes I already had to resort to assert norm. Rare cases, but already encountered that beast. Okay.
So after computing, we just have this simple goal, right? That 5 to 4 is equal to 5 to 4 to 8 is equal to itself, and then C3 can accept the definition. Something that we might like to have, which I'm almost done with having it working. I think this is working at maybe a bit of catching a lucky break, is that this part was a bit of guessing, right? We needed to find out that, okay, we need the fact that x is less than 19, so pow2 of x is less than pow2 19. But okay, we need to think of that, and then we also need to call it here with this precise argument, and it permeates through the whole proof, right? If we need many of these facts, we're going to have a bunch of calls, and they're going to pollute the SMT context, and we're going to have just like one big monolithic thing. So I'm working on a using lemma tactic, which is really just derived. It's nothing primitive at all. But when you call it, say, inside this assertion, you call using lemma of some particular lemma, it brings it into the local context. So it can use it to prove this particular goal. And you don't have to give it the arguments. It's just saying, okay, in your proof of this fact, use this lemma as much as you want. And you can possibly use others, right? In this case, it only needs, this one. But it's still not working so well, and this is in a branch, so don't try to use it right now. I'll let you know when it's available.
If I may, this is what allows you to keep some facts out of general context and keep your lemma context clean, right? Like whatever you are putting into this by begin end will not get above it, and the context of the big lemma will not.
Yeah. So begin and end are actually just fancy parentheses, right?
I know.
But you are right in that what's going inside here, that's a meta program, and it's not affecting anything that happens outside of it. Because this assertion gets split away from the main verification condition, and we handle it independently of all the rest. So yes, it is a way of taming the local context in a way and making it more well behaved.
This decreases the amount of litter in the context of big lemmas.
Right.
Like whenever you, for example, invoke some lemma that gives you a for all fact, it very well leads to a combinatorial explosion of facts. So if you instead wrap that into an assert by call, your proof context will get cleaner. Do I take it right?
Absolutely. That's one of the use cases for it. Yes.
Yeah. Thank you.
So okay, just a few examples of inspecting syntax. For example, here's a trivial proof, of course, but of a conjunction. We need to prove a conjunction, and metaprograms can actually find out what they're trying to prove and act accordingly. So, for instance, this example here is inspecting the current goal. This could have been written a bit more idiomatically like this. So, current formula looks at the current goal that we need to prove and gives you like a nice representation on the formula type, which maybe you can see below but it's in F-star reflection formula. And it gives you like a nice representation. And in this case, it's there's an AND constructor for conjunctions. And so in this case, we run this metaprogram, and we get this message saying, hey, it's a conjunction because this case matched. And then we do nothing because the code is trivial, so we just give it to C3. But if it was something else, so let's say maybe this was a disjunction, then this program will fail. This is raising an exception, and it's not being caught. So F-star is saying, no, try again. And there's similar constructors for every other kind of thing, like for implications here. So to comfortably inspect goals in a way. And then you can define stuff like, let's say this simple blow up tactic that will just split your goal. Like if it's a conjunction, it will split it. If it's an introduction, an implication, it will introduce the things and just give you a bunch of tiny goals. So for instance, in this small example here, we call this blow up tactic, and then we print the final state, and we have 3 sub goals that we need to prove. All of them are trivial because one is true and the other one has a false premise. But the important fact is that you can split different things and act accordingly on different parts of the thing you want to prove. So maybe only one of these needs like canonicalization, for instance, and all of the others can go to the SMT solver as they are. So I see I'm taking a long time, so I think I'm gonna go a bit faster here and then show you an example of canonicalization, a more interesting example of canonicalization. Otherwise, if there's anything in the chat, Tio, let me know, or anyone, yes.
Right, yeah.
Sorry, can I ask a really quick question?
Yeah.
This is really basic. So when you go to the match current formula thing,
yeah.
I'm just interpreting this using my knowledge of Coq. Is like when you do match goal, like the thing you're matching is not like literally an AND, but it's like squash of an AND, right? So does current formula like unroll these squashes for you or something?
Correct, yes. So the primitive is core goal or something similar to that. That gives you a term. But this core formula is a pure function that works on terms that will give you like a nicer view on it.
I see. Okay.
For instance, it's detecting that it's an application of a head, that it's the AND symbol to 2 things, and then giving you these subterms of it.
I got it.
Thanks. So okay, in the library there are a bunch of canonicalization tactics already defined. For instance, there's this module for canonicalizing expressions of a commutative semi-ring. When it's for integers, which is the most common use case, it actually already defines this in semi-ring tactic, which you can readily use for complex expressions. So for instance, in this test here, we're trying to prove that this thing here with a multiplication here is equal to this one, which is just the same thing unfolded. If we call in semi-ring, it will just automatically take care of everything and put it in normal form, and both sides are then trivially equal. And in fact, I think that I can call reflexivity here. So trefl is the reflexivity tactic, and I think these 2 are syntactically equal, so they should go through. Yeah, so there we go. And we proved this without using C3, right? So this happened completely within F-star via this tactic, which is a huge thing, and we could inspect later, or we could inspect at some point. But yeah, and here's the lemma that I showed you in the slides of this this function from poly 1305. Again, we call this canon semi-ring NCR. This is just an alias for that. This is really just defined as, well, doesn't matter, but it's defined as canon semi-ring NCR. So this lemma is really just doing the same thing. And so I think, well, here are some examples of metaprogramming of generating some functions from types. So for instance, this is generating a function that matches on a, oops, that's stuck, I think. This is generating a function that matches on this enum type and gives you a different number for each case, which is the basic idea of the printer that is defined actually in this file, examples tactics printer. So that there you can see like a rather semi-big tactic that descends on the syntax of the type and generates a printer for it. Yeah, so I think I want to show also, because I think Alex, you've been asking about this. This is a small toy example of canonicalizing with with an equivalence relation, which we already have like some basic support for commutative monoids with some equivalence relation. So this is running a slightly modified version of that module, but really very slightly modified. And I'll get that to master when this is starting to work again. But here I'm defining like integers. Yeah.
Yeah, there is a question maybe about when exactly the things are sent to Z3.
Okay, that's a good question actually.
Because I think when you use dump, it still sends stuff to Z3. So like when you use trefl, why doesn't it send it to Z3?
Okay, yeah, I didn't really show that it didn't send it to C3. So here's the thing. When we see goals in this, let's maybe put a few more dumps here. At any point, we can just stop, and every remaining goal would just be encoded and sent to C3 as is, right? But if there are no goals remaining, then we don't call C3. But it happens at the end. Like once the tactic has finished running, then all of the missing goals, the ones that are irrelevant, in case that means anything, the ones that are for proofs and not for terms, are sent to C3 like one at a time. And there's no way currently to like ask C3 to say to check if the goal is provable, and if not, try again or something. It really just happens at the end. But in this case, after the TOREFL, so here at this point, in the DOM2, we have this trivial equality, and after the TOREFL, so TOREFL unifies these two sides, and if they unify, like F starts unifier, then just solves the goal trivially. And in this case, we have no more goals. So nothing from this tactic is sent to C3. In fact, we could try this. There's an option to say, I do not want to use the SMT solver. I'm not exactly sure if this will work because maybe we need the fact that 2 is non-zero or something from C3. Okay, no. So this entire definition we just checked without the use of C3 at all. Like not even for the web formless of this function or the goals remaining for the tactic or anything like that. This just worked out of the box. So this no SMT option does exactly that. It forbids all calls to the SMT solver. Does that make sense?
Thanks. Yeah, thanks.
Oops. And okay, here's maybe a toy example, but of canonicalizing with some equivalence relation. So there's already this module, canon monoid simple equiv. Here I have a slightly modified version, but really, like I just deleted a line. So the thing that this module allows is you can define an equivalence relation, say on integers, and here I'm saying equivalence modulo 10, right? So if x modulo 10 is the same as y modulo 10, then I consider an equivalent. It's trivial to show that this is reflexive, transitive, and symmetric. And then we can define a commutative monoid with addition over this equivalence relation. And it's actually a ring, right? But I'm just defining the monoid here. And then using this canon monoid tactic, so here I'm defining a custom tactic, right? When I call canon 10, well, it does a few dumps, so I can show you what's going on. But it calls into this canon monoid by saying, this is my my equivalence relation, and this is the commutative monoid that I'm working on. So please canonicalize expressions belonging to that. And then we do some normalization, which I think really should be done by the tactic. This is probably something that to be fixed. But that will allow me to prove many of these goals trivially without the SMT. So for instance, in this case of A equals A, well, there's really nothing much to do there, right? The canonicalizer will just do nothing and just give me A equals A, which is trivial. In this case, we have A plus B plus C and C plus A plus B in this case. So some commutativity and associativity is needed. And as you can see before, we have the thing as we wrote it, and after we have the same, both of them are canonicalized. Here's also an example involving 0. The 0 will, of course, disappear. The canonicalization tactic.
Sorry,
the
one question.
Mm-hmm.
I just saw the overloaded. What was the scientific name for this provable equality operator? The double equals.
Oh yeah, just defining. I could really just...
it, and then you call the canonicalization tactic. Does it get
the syntactic hack? I could just do this. There's nothing deep about it.
No. I know. I mean, how do you tell the tactic that you are going to use a custom relation? Is it that the modified part you were talking about in
It's
the
here.
beginning that you slightly? All right. So you pass the canon monoid that is using these special equivalents.
Yes,
to
the
the
CQ
tactic.
file is a special equivalence, and it's defined here.
I know. Okay, this is what you pass to tactic to tell it that you are going to operate with custom equivalents. And that particular tactic that is monoid
Yes,
something.
this is not a genetic thing at all, right? I'm actually just making use of one module for canonicalizing commutative monoids with an equivalence relation. As soon as you want to use something else, you need to write such a tactic. It's not really like you can just say, I'm working modulo some equivalence relation and be done with it. It's actually a quite classic problem in type theory, working with setoids and this kind of thing.
Yes, fair. Okay.
So anyway, this was, I think Emacs crashes for me once in a while. I'm not sure if it happens to anyone else. So okay, this one, it proved like trivially from reflexivity because it cancels the zeros and associates. And even if, the tactic cannot do all work that there is to be done, for instance, here I have a plus 10, which modulo 10 is really a plus 0, but the tactic has no way a priori of realizing that. And one times a, well, this 1 times is not really part of the monoid. So the tactic doesn't really do much here besides taking the 0 away. But it still does something, and you can still call the SMT solver or further tactics on it, right, to further simplify the goal. And even in this more complex stuff, it will do what it can, and then just present you a simplified goal. So yeah, I think, well, I'm pretty over time, I guess. So I guess whatever anyone would like to ask something or something's missing. I guess something that I didn't mention a lot is how to inspect syntax and work on it and this stuff. There is a section written on it, a pretty big section, I think, on this chapter that I uploaded to the channel, if you want. And there's a ton of examples, but I thought it wouldn't be super interesting for the talk. So maybe that's it. Yeah.
Thank you. Any questions?
I'm just making sure I understand it right. Currently, there is no semi-ring tactics that work with custom equivalence relations, because if there is none yet, then I'm going to develop one. Like I'm currently writing the abstract algebra stuff, a lot of abstract algebra stuff, and a lot of my proofs therefore look ugly. Just similar to the way you showed in the beginning of your talk, when you spoke of 41 associativity and the rest steps. It's just that some of my proofs go way beyond just mere 40 steps of invocations. Some are quite a lot heavier than that. And I'll be reworking my proofs so that they do not take pages of lemmas. And I just want to make sure that there is currently no ready semi-ring tactic that is adapted to custom equivalence, right?
Yep, correct. There is no.
Because I already saw there are monoid tactics which you just used that use custom equivalence, right? But no rings.
A single one, yes.
But no rings. All right.
No,
Then
we have rings, no custom equivalence. Sorry, we have semi-rings, but
no custom equivalence.
Right.
Only the provable equivalence that is double equals the system one. Yes. Because I somehow perceive that F star handles this equivalence better than custom ones. Like if I even if I provide for all styled facts into context, FStar proves stuff about this system equivalence way more readily than it does with my custom equivalence, even if all the same facts are in context. I checked that.
Yeah, I believe that pretty much any proof assistant will work better with propositional equality than just a custom relation.
So
even if you provide all the consequences, the people that work in COG and Lean have this thing that they call setoid hell, for when you need to carry equivalences around all the time and call congruences and all this.
Setoid hell.
So it's not a trivial problem
All
to
right.
work modulo equivalence.
So it was not just me, but indeed that was a problem with custom equivalence being processed way less easily than the provable one. All right, thank you. But probably I'll have much more questions on this topic. I'll probably ask you later about it if you don't mind me, because there will be a lot of questions. I can already assure that. I'll do my best to understand whatever I can without bothering you guys. But eventually I'll probably have more questions. I'm going to come up with algebra system that goes far beyond just basic stuff like rings, modules, and whichever is told in algebra 1 currently. So at some point I will surely need mechanisms to ease my proofs. Like when I constructed the field of fractions, some of the lemmas approached hundreds of steps. And this is actually quite, how do I say it? Quite demanding in both sanity and willpower. Like by the end of the proof, I was quite wasted. So I'll have a lot of questions on tactics and how do I simplify my stuff. Yeah, I hope you don't mind me. I'll ask a lot of questions on that matter later. Other than that, thank you very much. I enjoyed the talk.
Okay, welcome. I now see that there's a bunch of comments in the chat. Sorry, I couldn't see them when I was presenting.
Yeah, I mean, we tried to answer those and then just forwarded one.
Okay, thanks.
I also had one question. I guess maybe we have a bit of time.
Yeah.
I was wondering if you, like the TC resolves then is something that is almost user, or you said user defined, right? So could you define or redefine your own TC resolve to add some hints instead of just using instances? You can say if you want to fill a goal that looks like this, then you can apply this tactic. This is something you can do in COG, and I don't know if you can do it, but it seems like it should be doable with your settings. So
you can do it as long as you tag the implicit argument with the tactic that you want to use to solve it. The only thing native about type classes in a way is just a syntax, like class and instance and the fancy brace bar, and that's all. So if you were to declare, I guess you could even declare like a custom type that hides this implicit argument, and then just use this custom type that you define in your own program. And then you write whatever tactic you want, right? And you can look at how TC resolve is implemented, which is really just quite naive currently. It just looks up in the environment everything that is marked with some given attribute, which is TC instance, and it just looks to see what can be applied. And that's really all. Then you have all of the reflection capabilities at your disposal to do whatever you want.
Okay, great. So I guess if there is no more questions, we can thank you again. This was a great talk.
Thanks, Guido.
Welcome. Thanks for
Thanks.